Okay, so welcome to this next video in which we are discussing the receptor tyrosine kinases. Okay, right. So we're currently in the process of discussing phosphoinositide 3 kinase enzymes, or PI3 kinase enzymes. Okay, so now let's start to discuss the PI3 kinase enzymes themselves. So, the first thing to say is that PI3 kinase enzymes are enzymes which phosphorylate phosphoinositides. Okay, so they are going to phosphorylate phosphoinositides on the third carbon of inositol molecules. Okay, so they are going to stick phosphate groups onto the alcohol group that comes off the third carbon. That's why it's called phosphoinositide 3 kinase. Okay, so that's what this 3 here refers to. It refers to the fact that we are going to stick a phosphate group coming off the alcohol group of the third carbon of the inositol ring. Okay, right. Now, phosphoinositide 3 kinase enzymes can be further divided into 3 families. Okay, so there are type 1 phosphoinositide 3 kinases, then there are type 2 phosphoinositide 3 kinases, and there are type 3 phosphoinositide 3 kinases. Okay, so let's talk about what these 3 classes of phosphoinositide 3 kinase enzymes do. Okay, so we'll start with the type 1s, which is the type we're going to be really interested in. Okay, so type 1s have a substrate which is phosphatidyl inositol 4,5-bisphosphate. So the difference between these 3 types of phosphoinositide 3 kinase enzymes is that they all work on different phosphoinositides. Okay, so they all add phosphate groups onto the third alcohol group of the inositol ring, but they work on different starting materials, basically. So type 1s all start with phosphatidyl inositol 4,5-bisphosphate, PI45P2 here. So let's just draw it out once again. So here is our long-chain carboxylic acids, okay, attached to our glycerol molecule here. Then we've got our phosphate group coming off the glycerol molecule and completing the phosphatidic acid molecule. And then we've got our inositol ring attached via phosphester link to the phosphate group of the phosphatidic acid molecule, and then we've attached phosphate groups onto the alcohol groups that come off the 4th and the 5th carbons of the inositol ring. Now, what type 1 phosphoinositide 3 kinase enzymes are going to do is they're then going to take these molecules, which are usually just abbreviated to PIP2 molecules or PIP2 molecules. So usually we drop the 4,5 because usually when people write PIP2 like this, it's generally accepted that usually they mean that these phosphate groups are on the 4th and the 5th carbons. Okay, if they weren't, generally people would make it very obvious that they meant something different by putting brackets here and maybe having 3,4-bisphosphate or something like that. Okay, so usually if people don't specify which carbons of the inositol ring the phosphate groups are coming off, you can assume it's 4,5. Okay, so they're going to take this as their starting material, and they're then going to produce a molecule which is now going to have 3 phosphate groups coming off the inositol ring if you don't count this first one here. Okay, so here's our inositol ring now. Okay, we've got a phosphate group coming off the 5th one, a phosphate group coming off the 4th, and now also a phosphate group coming off the 3rd. Okay, so this type of phosphoinositide 3 kinase enzymes is the type that we're going to be very, very interested in. Okay, so here are the long-chain carboxylic acid molecules. Here is the inositol molecule. Okay, now we've got our phosphate groups all in purple here. Okay, so our final molecule here is known as phosphatidyl inositol, of course, because we still have the phosphatidyl, whoops, not like that. We still have the phosphatidyl inositol molecule as our backbone, okay, consisting of the phosphatidic acid attached to the myoinositol ring. Okay, but now we have 3 phosphate groups coming off, so this is, let me just move it up a little bit, 3, 4, 5 trisphosphate. So we have phosphate groups coming off the 3rd, the 4th, and the 5th carbons. So it's phosphatidylinositol 3, 4, 5, and then trisphosphate, because you have 3 phosphate groups. Okay, right. And for short, this would be abbreviated as PI for phosphatidylinositol, and then you put brackets 3, 4, 5, and then close brackets P3, like so. Okay, now, people will often abbreviate this further, just like PI45P2 up here is usually abbreviated just to PIP2 or PIP2. Usually people will just abbreviate PI345P3 to PIP3. Okay. Usually, if people do not clarify which carbons of the inositol ring the phosphate groups are coming off, you can assume that if it's got 3 phosphate groups coming off it, they are coming off the 3rd, the 4th, and the 5th carbons. Okay, this is the main form of phosphatidylinositol with 3 phosphate groups then additionally added on. Okay, right. So that's what type 1 phosphoinositide 3 kinases do. Now those are going to be the ones that we are going to study, okay, with regards to the receptor tyrosine kinases. The others are more niche, but I'm just going to mention what the difference is between the substrate specificities, just so that you have some comprehension. Okay, right. So type 2 phosphoinositide 3 kinases, these work on phosphatidylinositol 4-phosphate molecules. Okay, so their substrate is phosphatidylinositol 4-phosphate. So let's just redraw this out. So here is our phosphatidic acid molecule. Here is our inositol ring here. And then we've got a phosphate group coming off the 4th carbon of the inositol ring. So here are the phosphate groups in purple. Here is the inositol ring in blue. Okay. Here is the glycerol molecule in green, and here are the long-chain carboxylic acids in orange. Okay, so what type 2 phosphoinositide 3 kinase enzymes are going to do is they're going to phosphorylate the alcohol group that comes off the 3rd carbon of the inositol ring, and therefore convert this into phosphatidylinositol 3,4-bisphosphate. Okay, so here's our phosphatidic acid molecule. Here's our inositol ring, and now we've got phosphate groups coming off the 4th and now also the 3rd phosphate. Okay, so here are our phosphate groups in purple. Here in blue is our inositol ring. Okay, here in green is our glycerol molecule. And then in orange, here are our long-chain carboxylic acids. Okay, so this is PI4P, phosphatidylinositol 4-phosphate. This now is phosphatidylinositol, and now it's 3,4-bisphosphate. Now, you would not abbreviate this to PIP2. Okay, if you use PIP2, people will assume you mean phosphatidylinositol 4,5-bisphosphate. They will not assume that you mean phosphatidylinositol 3,4-bisphosphate. Okay, so you do need to spell this one out and tell us exactly which carbons the phosphate groups are coming off in this case. Okay, so that's another phosphoinositide where you've got 2 phosphate groups coming off the phosphatidylinositol molecule. Okay, right. Finally, type 3 phosphoinositide 3 kinase enzymes are going to work on phosphatidylinositol itself. Okay, so here we have our phosphatidylinositol molecule, like so. So we'll colour it in once again. So here are our long-chain carboxylic acids in orange. Here's our glycerol molecule in green. Here's our phosphate group coming off the 3rd carbon of the glycerol molecule, and here's our inositol ring in blue. Okay, so the substrate for type 3 phosphoinositide 3 kinase enzymes is phosphatidylinositol itself. Okay, and what the phosphoinositide 3 kinase of the type 3 is going to do is it's going to phosphorylate the 3rd carbon of the inositol ring and convert this into phosphatidylinositol 3-phosphate, like so. Okay, so here are the phosphate groups, and then in blue here is the inositol ring. Okay, and then here are the long-chain carboxylic acids, and here is the glycerol molecule in green here. Okay, so this then now is phosphatidylinositol 3-phosphate, PI3P. Okay, right. So, those are the 3 different types of phosphoinositide 3 kinases. We are not going to say anything more about type 2 and type 3. We are going to focus our attention completely now on the type 1 PI3 kinase enzymes. Okay, so let's study the structure of these enzymes in a little bit more detail. So firstly, what we need to discuss is that they actually are heterodimers. They are 2 separate polypeptides stuck together, okay, like so. There is one regulatory subunit, which I'll denote R here, and then there is one catalytic subunit. Okay, so let's write a little bit of this down. So PI3 kinase enzymes of the type 1 are heterodimers. Okay, hetero means different, dimer means 2-membered structure rather. Okay, this is a 2-membered structure. It's got 2 proteins making it up, which are different. Okay, that's why it's called a heterodimer. Okay, now one of these is the catalytic subunit, which is this one that I'm now highlighting in green here. So this is the catalytic subunit. Okay, and then the other is the regulatory subunit, which I'll now highlight in red here. Okay, right. And together they make the full PI3 kinase enzyme. Now, it's a little bit more complicated than that, because what would be beautifully simple is if there was just one catalytic subunit of type 1 phosphoinositide 3 kinase enzymes and just one regulatory subunit. That would be the beautiful scenario. We could call it the catalytic subunit of type 1 PI3 kinase. We could call this the regulatory subunit of type 1 PI3 kinase, but it's not so. There are multiple catalytic subunits, and then there are multiple regulatory subunits. Okay, so let's start off with the catalytic subunits. So there are 4 different catalytic subunits of phosphoinositide 3 kinase type 1 enzymes. Okay, so these are known as P110 alpha, okay, P110 beta, and then we continue on down the Greek alphabet. P110 gamma, and then finally P110 delta. Now, before I come on to the regulatory subunits, what I should say is that the whole type 1 PI3 kinase enzyme is named according to which catalytic subunit it has. Okay, so we do not care what the regulatory subunit is when we name our PI3 kinase type 1. Okay, you just look at the alpha subunit. So, people name up the PI3 kinase type 1 enzymes like so. Okay, if they're being good, they will put a type 1 out in the front here. If they're being bad, they'll just put PI3 kinase, and they'll assume that if they don't clarify that it's not a type 1 PI3 kinase, that you assume that it is a type 1 PI3 kinase. So the most important PI3 kinase enzymes are the type 1s. So just as you could get away with abbreviating PI45P2 to PIP2, and everyone knew what you meant, usually if you just put PI3 kinase, people will assume you mean a type 1 PI3 kinase. Okay, but if you're being good, you'll say explicitly that we're talking about a type 1 PI3 kinase. Okay, so people will call these type 1 PI3 kinases then by what catalytic subunit they have, and therefore there is type 1 PI3 kinase alpha, there is type 1 PI3 kinase beta, there is type 1 PI3 kinase gamma, and there is type 1 PI3 kinase delta. And this just refers to which of the catalytic subunits you actually have within your heterodimer. So, if you are a PI3 kinase alpha, I don't care what your regulatory subunit is, but your catalytic subunit is P110 alpha. Okay, same for beta, same for gamma, same for delta. Okay, right. So, that's the naming then of the type 1 PI3 kinases. Okay, now, the type 1 PI3 kinase enzymes are subdivided further, and there's good reason for this. So I'll get another piece of paper and explain this to you. Okay, so we subdivide the type 1 PI3 kinases further into the type 1As and the type 1Bs. Okay, so the type 1A phosphoinositide 3 kinase enzymes are phosphoinositide 3 kinase alpha, and remember I'm now being bad, I'm not putting the type 1 in front. Okay, then we've got PI3 kinase beta and PI3 kinase delta is the final one. The type 1B is the PI3 kinase gamma. Okay, so remember, all this means at the moment is that they have different catalytic subunits. This one has the P110 gamma subunit as its catalytic subunit, whereas these three have P110 alpha, P110 beta, and P110 gamma. Okay, right. Now, these ones, the type 1A phosphoinositide 3 kinase enzymes, these are going to be the ones that are actually activated by receptor tyrosine kinases. The type 1Bs are not activated by receptor tyrosine kinases. They're activated by the beta-gamma subunits of heterotrimeric G proteins, and we're not going to go into them. Okay, so just to finish our discussion of type 1 PI3 kinase enzymes then, I want to talk about the regulatory subunits. So remember, we have these two subunits in all type 1 PI3 kinase enzymes. We have a catalytic subunit, which is one of those four, and then a regulatory subunit. Now, let's discuss the regulatory subunit then. Okay, so the regulatory subunit that you use differs depending on whether you are a type 1A PI3 kinase or a type 1B PI3 kinase. So this just becomes more and more complex. Okay, so if you are a type 1A PI3 kinase, you are going to be regulated by receptor tyrosine kinases. Okay, now how do receptor tyrosine kinases activate you? Well, they interact with your regulatory subunit. They don't interact with the catalytic subunit. They activate the regulatory subunit. Okay, if you're a type 1B, you're going to be activated by the beta-gamma complex of heterotrimeric G proteins. Okay, and once again, they will act on your regulatory subunit. So it therefore makes sense that these type 1B PI3 kinase enzymes are going to have different regulatory subunits to the type 1A PI3 kinase enzymes. Okay, so let's now talk about the regulatory subunits that type 1A PI3 kinase enzymes have. Okay, so all of these type 1A regulatory subunits are going to have a special domain for binding to phosphotyrosine residues. Okay, and this is going to be an SH2 domain. Okay, they actually have two of these, but in fact, I might just show this. There we go, we've now got two SH2 domains. Okay, so remember, SH2 domains are Sark homology 2 domains, and they bind to phosphotyrosine residues, which are on the intracellular aspect of our receptor tyrosine kinase dimer. Okay, right, so let's now study these type 1A regulatory subunits then. So there are 5 of these. Now, for short, they are all known as the P85 regulatory subunits. So there are actually 5 different P85 regulatory subunits. So people will often just write P85 as the regulatory subunit of a type 1A PI3 kinase enzyme. However, there are actually 5 different P85 type regulatory subunits. Okay, so what are the names of these 5 different P85 type regulatory subunits? Well, there is P50 alpha, firstly. Then there is P55 alpha and also P55 gamma. Okay, so P55 alpha and P55 gamma are the second and third. And then finally, there are some that are actually called P85s themselves. And there is P85 alpha and then also P85 beta. Okay, so these are the 5 different P85 type regulatory subunits here, okay, in red, like so. These are the regulatory subunits that you will have if your catalytic subunit is either P110 alpha, P110 beta or P110 delta. Okay, and all of those are type 1A PI3 kinase enzymes. They'll be named according to which catalytic subunit they have, so you'll have either PI3 kinase alpha, PI3 kinase beta, PI3 kinase delta. You don't mention which of these 5 regulatory subunits you have, you just call it a P85 type regulatory subunit, but it could vary which one it is. Okay, they are going to be regulated by receptor tyrosine kinases, so we'll come back to those. Just for a complete story, I would just like to mention the type 1b regulatory subunits as well. So if you're a type 1b PI3 kinase enzyme, then your catalytic subunit, we know what it is, it's P110 gamma. Okay, and you are automatically a PI3 kinase gamma enzyme. But your regulatory subunit can either be P101 or it can be something called P84. Okay, so there are 2 options there, P101 or P84. Okay, and this time you do not have an SH2 domain in. Okay, so you do not become activated by receptor tyrosine kinases. So these type 1 PI3 kinase enzymes are not going to be of interest to us. So we are specifically interested in these 3 type 1A PI3 kinase enzymes, which are these enzymes which are going to phosphorylate phosphatidylainositol 4,5-bisphosphate molecules to create phosphatidylainositol 3,4,5-bisphosphate molecules, and which are bound to regulatory subunits which have 2 SH2 domains and are therefore going to be activated by receptor tyrosine kinases. So let's now draw this activation. Okay, so let's draw our receptor tyrosine kinase out once again. Okay, so here's our amino group. Okay, here's our ligand binding domain, which will be dimerized with the ligand binding domain of another receptor tyrosine kinase, like so. They'll then both have their membrane spanning alpha helices, their kinase domains intracellularly, like so. Okay, and then they'll have their carboxylic acid terminals intracellularly. Okay, and then of course ligand has had to bind to the ligand binding domains in order to get them to dimerize like this. Okay, so here is the ligand molecules bound to the ligand binding domains, which are in orange here. Okay, and here then are the tyrosine kinase domains in blue here. Okay, and of course what's then happened is we've had trans-autophosphorylation, where the tyrosine kinase domain of one has phosphorylated tyrosine residues on the other, and the other has reciprocated. This has then activated those tyrosine kinase domains, and they've then phosphorylated tyrosine residues in the cytoplasmic domain of the opposite tyrosine kinase receptor. Okay, right. And now what's going to happen is we're going to get the activation of these type 1A PI3 kinase enzymes. Okay, so initially the type 1A PI3 kinase enzymes are within the cytoplasm. Okay, so here we have our inactive type 1A PI3 kinase enzyme. Okay, so remember the catalytic subunit will either be P110 alpha, or it will be P110 beta, or it will be P110 delta. Okay, so we'll colour in the P110 subunit in vivid purple here. Then the regulatory subunit will be P85 type. Okay, so there'll be one of these 5 that we've discussed, and the important thing is that it will have 2 of these SH2 domains. Now, once the phosphotyrosine residues are produced on the intracellular aspect of our receptor tyrosine kinase, the type 1A PI3 kinase enzyme is going to now translocate from the cytoplasm to the underside of the phospholipid bilayer, and the way it will do this is quite simple. These SH2 domains of the regulatory subunit of the PI3 kinase enzyme are going to bind to the phosphotyrosine residues on the intracellular aspect of the receptor tyrosine kinase. Okay, so here we have our 2 SH2 domains on our P85 type regulatory subunit. Okay, here. And when the P85 binds to these phosphotyrosine residues, this has two effects. Okay, firstly, it has just relocalized the complex. Okay, so it's brought the complex up to the underside of the phospholipid bilayer. Now, why is that so important? Well, it's because the substrate for PI3 kinase enzymes of the type 1 form is phosphatidylinosytyl 4,5-bisphosphate. Now, where is phosphatidylinosytyl 4,5-bisphosphate? Well, it's in the cell membrane. It's not a particularly common phospholipid to have within the cell membrane, but you do have some of it within the cell membrane. Okay, so here is our substrate for our type 1 PI3 kinase enzyme. There are the long-chain carboxylic acids, which will anchor it into the phospholipid bilayer. There's the glycerol molecule. Here are the free phosphate groups here. And then we have our inositol ring, okay, which will form part of the head of the phospholipid and is dangling into the cytoplasm. Okay, so we've firstly moved it to a place where it will be in contact with its substrate here, which is PI45P2 here. Okay, in addition, when the P85 binds to the phosphotyrosine residues on our receptor tyrosine kinase dimer here, what will happen is it will also loosen its interaction with P110. Okay, now P85 binding very strongly to P110 does inhibit the catalytic activity of P110. Okay, so this is the active enzyme which can phosphorylate that third carbon of PI45-bisphosphate molecules. Okay, now it's not true to say that before it binds here that it's not active. This enzyme in the cytoplasm does have some activity, okay, but it's just in the wrong place. It can't find its substrate, so there's no point on it having activity. It doesn't actually do anything. So do not underestimate the importance of just merely translocating it up to the underside of the phospholipid bilayer. But not only do you just translocate it, you also do activate it to some extent. So both of these things are going to play roles together, basically. They're both going to work together to mean that this P110 is now going to start converting PI45-bisphosphate molecules into PI345 trisphosphate molecules. Okay, so what's going to happen is, because of both of those factors, because of the translocation from the cytoplasm to the underside of the phospholipid bilayer, and because of the change in the interaction between P85 type regulatory subunit and the P110 catalytic subunit, P110 is now going to gain catalytic activity, and it's going to work on the PI45 bisphosphate molecule, and it's going to phosphorylate it to PI345 trisphosphate molecules. Okay, so we're going to convert it from phosphatidylinosytyl 4,5-bisphosphate into phosphatidylinosytyl 3,4,5 trisphosphate. And of course, once you've done this conversion, the molecule will remain within the phospholipid bilayer. Okay, so here's our inositol ring in blue here. Okay, here are the phosphate groups coming off the inositol ring here. Okay, here is the glycerol molecule in green, and here are the long-chain carboxylic acids still attaching it into the underside of the phospholipid bilayer. Okay, so this is phosphatidylinosytyl 3,4,5 bisphosphate, and these two are so famous that you can get away with just abbreviating them to PIP3 for PI345P3 and PIP2 for PI45P2. Okay, right. Now, this enzyme is going to produce loads of this PIP3, and usually you have absolutely no PIP3 in the membrane, and the reason for that is that there are enzymes which break PIP3 down, basically. Okay, so a good example of that is the phosphatase and tensin homolog enzyme, okay, often just abbreviated to P10, which removes the phosphate group from the third carbon of the inositol ring and returns it back to PIP2 here. Okay, so P10 is an enzyme which will be scouring the membrane looking for PIP P3 molecules and breaking them down. Okay, so this is one of the reasons that you have very little PIP3, if not none, in the cell membrane usually. Okay, so this stands for the phosphatase and tensin homolog enzyme. So the P is for phosphatase and then the 10 is for tensin homolog. Okay, right. So basically, once you activate this type 1A phosphoinositide 3 kinase enzyme by these phosphotyrosine residues on the intracellular aspect of the receptor tyrosine kinase dimer, it is transiently going to produce a spike in the level of PIP3 within the cell membrane, basically, and this transient rise in the levels of PIP3 in the cell membrane is going to trigger the activation of the downstream pathways. Okay, and we'll see this in the next video.